Well, hi everyone. Welcome back to lecture 2 about quantum computing, which is going to be a bunch about quantum algorithms, but actually a few more things as well. Yes, we're going to have the fun of changing slides again. Hold on. There we go. So what we talked about yesterday, I'm not really going to go through it in any detail, is we went through some building blocks that one needs to think about quantum computing. In particular, I introduced qubits. Then we talked about how you can actually operate on qubits with quantum gates, how you might combine those quantum gates into quantum circuits. And then we finished up with some discussion about the various different technologies that one can actually use to realize qubits. So that's the outline. I noticed my red boxes moved slightly, but what we're going to be talking about today is really about quantum computers of today and quantum algorithms. And then there will be also some discussion about error correction. I'm also going to talk a bit about quantum advantage and various things like that. And today it's going to be a mix in some sense because we don't have much time. Things are going to be a little bit at a sort of superficial level. And that's because I really wanted to save time for tomorrow where we can spend some time discussing how we might apply these things to HEP. So to mitigate that, I've tried to include lots of links, and I'll post the slides just after to the webpage so that you can find out more information if any of these topics gets you particularly interested. Thanks for all the questions yesterday. They were great. I did want to respond to one of them. I've put together a slide. It was also in yesterday's slides as well, but now it's been expanded and tidied up a bit with some further resources in case you're interested to learn more. There are two categories. There are a bunch of online resources, and then there are also some books. And I've tried to include books at various different levels. So depending on what you're after, if you're after some light reading for the evening, or if you want to take a course in quantum computation, hopefully there's one that would really serve that need for you. So after that, let's move on to today. Yep, we're going to start with talking about quantum computers today. Then we're going to talk about some of the really key quantum algorithms. And I've linked here a nice review article because quantum algorithms are really, in some sense, at the core of quantum computation. That's why people are particularly excited about quantum computers. And the three we're going to talk about are the quantum Fourier transform, which is pretty simple if we all know Fourier transforms very well. But it turns out that one is a workhorse of the quantum algorithms and really used in various different places. Then we'll talk about Shor's factoring algorithm, which was the one that got everyone excited / nervous about quantum computers. And then finally, we'll talk about the quantum search, which is Grover or Grover-Long algorithm. A few words about quantum programming languages, if you want to go and try something out. A bit about quantum error correction, some progress in quantum simulation, and then finally we'll round it out with a talk about quantum advantage. So let's get started with the sort of quantum computers of today. And here's the acronym, which of course I could not remember yesterday when I was giving the lecture. And that is the NISQ era. It's one that was created by John Preskill. And the NISQ era is the noisy intermediate scale quantum era. And that's really meant to talk about where we are today, where we have quantum computers with a handful of qubits, but are very noisy, which makes them really tricky to actually use for any sort of practical means. And here's a set of pictures for some of them. There is the IBM quantum hummingbird, which has 65 qubits. That's a picture of the chip. There is the D-Wave advantage. That's one of those quantum annealers, which has more than 5,000 qubits. The reason it's more than 5,000 is they tell you you'll have at least 5,000 qubits available if you want to use it. But there are actually a number of machines, and some of them have more. There's a photon supercomputer. This one's in China. It's at USTC, which is Zhejiang. And then there's Google Sycamore, which has 23 qubits. And we'll come back and talk about them a little bit more. Now, there used to be an awesome page on Wikipedia, which kind of kept a list of all the different quantum computers around. I think people have given up. Perhaps things are moving too fast. Because I noticed that some of the most recent ones in particular are missing from this page. But nonetheless, it's nice and it's useful. And it gives you a sort of scale of the various different things that are going on. There really are a number of different companies which are really building these various different quantum computers. And you can see some of the ones that I mentioned here. At the moment, there are actually more than 193 different quantum computing startups worldwide. And so it's really an area where there's this rapid development from various different countries. I lost my mouse again. Hold on. There we go. So there is one of the two that sort of perhaps maybe considered very well known are Google Sycamore and the various different bird-based IBM quantum computers. And I put them together here on a slide because both IBM and Google use those transmon superconducting qubits that we discussed. So it's a very similar use of the same qubit technology. On the top right there, that's an image both of Sycamore and also of the connectivity, which I'll come back to in a second. And the way that this computer is constructed, it's a 2D array of 54 transmon qubits. Now, if you hear and look at the various different articles about Sycamore, what you'll see is that it only has 53, and so you're wondering, why am I saying 54? Unfortunately, what happened is that one of the qubits simply didn't work. And so even though it was designed to have 54, there are actually only 53 which are functional. Now, if you look at that image of the connectivity on the top right, what you can see is that each of the individual qubits is coupled to 4 other qubits. And this is always one of the issues that's really important in quantum computers of today, because although we would like all qubits to be coupled to all other qubits, that would really allow us to do, the most complex type of things, algorithms on a quantum computer, it turns out to be very difficult to do that. And so typically there is some sort of limited coupling. The other point is that if you decrease the amount of coupling, you can also control things like the noise, etc., in the quantum computer. And so you need to know what this is, because it's not enough just to know how many qubits there are. You also need to know this coupling to know how you might actually go about implementing your quantum algorithm. Now, the way that this is made out of uses aluminium for metallization, and those Josephson junctions also uses indium bump bonds between the silicon wafers. Pretty much like most quantum computers, it needs to operate in a dilution refrigerator, and this one is at a temperature of 20 millikelvin. Now, the more recent chip, which came out, I think, last year, is this IBM Hummingbird. I tried to find you some more details about it. Unfortunately, as we were discussing yesterday, these are things that are coming out of companies, so there's often very limited information available. And it has, this is a picture of it. It has 65 qubits, and it has an interesting technique used for the readout. Essentially, this is another problem that one has, is as these number of qubits increases, becomes difficult to actually read out the information from all the individual qubits, because you end up having this tiny thing with all these different wires, kind of similar to how we have with our particle detectors. And so what they've done here with Hummingbird is they use this 8-to-1 readout, where they actually managed to read out 8 of them over one wire. And unfortunately, I didn't find any more details exactly how they did it. I assume it's some sort of algorithm where you can still recover the information that you need. On the right, there is a picture of the connectivity for Hummingbird, and in fact, I think many of the current IBM quantum computers. You can notice they're using this kind of hexagonal structure in how they would actually connect the qubits together. But in the end, it's pretty similar in terms of the limitations that we were discussing for Google. Now, the companies like to make some ambitious statements about their plans. And one of those basically is that they will be planning to actually double the number of qubits that they have every single year. So, they've had the 65 qubits from Hummingbird. They're planning to have 128 this year, and it's going to be 200 and something to do it. And then that will, of course, rapidly increase the scale of quantum computers. It'll be very interesting if they manage to do that, because, of course, that will mean that in a matter of a few years, we will have quantum computers that are significantly more powerful available for us. Fun fact, they're all named after birds to do it. And I actually linked there a very interesting blog by someone who's actually working on developing these computers. And it actually tells you some of the sort of more practical things about what it's actually like to develop them. So those are Sycamore and IBM, both made of transmon qubits. both in the scale of, many tens of qubits. This is really one of the state-of-the-art types of quantum computers. Now, another computer that was in the news basically at the end of last year is the one at the University of Science and Technology in China, which is the Zhuzhang Sanshu, which is actually named after an ancient Chinese book on mathematics. It translates into English as the 9 chapters on mathematical art. This one is completely different. You can see the image there on the bottom left. That's actually the computer itself. It is an optical quantum computer. So we're really thinking about using photons and their polarization as the qubits. And all the different pieces that you can see here, this consists of light sources, beam splitters, mirrors, and then 100 different photon detectors, which I think are just photomultiplier tubes. And the way that this is actually used is one uses repeated splitting and merging in order to obtain interference and to really build up the quantum state that they want. Now, this one is quite different in some sense than either Sycamore or the IBM computers. It's really a custom-built, non-programmable quantum computer, but it was designed, which it achieved, we'll come back to that later, to demonstrate quantum advantage. There are other people making programmable photonic computers. There's actually a Canadian company called Xanadu, and they've made an 8-qubit photonic quantum computer. And the idea is that they want to actually be able to sell that to people who want to have a quantum computer sitting in the lab. So that's why I was joking yesterday and saying that, yep, you can buy one if you want one at CERN. Of course, they're still small and still really under development to become a lot more powerful. Now, yesterday, there were a bunch of questions about trapped ion computers. So I added a slide just to try and address some of them. People were most interested in, how do we actually set up these gates? How do these actually work? Now, you have kind of 2 choices for trapped ion computers for how you set up the qubits. You can either use the ground and excited state, or maybe you want to actually use 2 hyperfine levels for the ground state. And here you need to do some laser cooling to reduce noise. Now, in order to get the information onto the qubits, you want to use optical pumping with a laser. And this is a common thing used in various different experiments that would also use trapped ions. And the fidelity here will be something greater than 99.9%. Then to do the operations, it's a little bit different, whether you want to do single or 2-qubit operations. For single qubit operations, what you want to do is to drive the atomic states with resonant optical or microwave fields. You can also, instead for the second one, you can also use the Raman transition to do that. Then for the 2-qubit operations, what you actually want to exploit is the charge interaction between the trapped ions. You want to excite one of the ions to oscillate. Sorry, just one second. And then induce the second to move. And then you want to carefully tune the field frequency to push the ions only if the qubit is in a specific state, and to ensure that you really maintain coherent excited motion. So and then once you're done, you need to measure. And so you apply a laser to the ion that couples to only 1 qubit state. And then, of course, this is going to emit some photons. And then you collect those with a photomultiplier tube. If you're interested in learning more, I added a couple different references where you can find some more details about how exactly trapped ion computers work. So I showed a version of this slide yesterday, but I want to say a bit more today. The current state-of-the-art examples of trapped ion computers come from Honeywell and IonQ. And we talked about the fact that the single qubit coherence is approximately 1 hour. They have very high single and double qubit fidelity. And they have this advantage, and that's this little yellow image that you can see here, which is actually showing you that you have this full connectivity between the different qubits. So 2 of the companies producing them, this is IonQ and Honeywell, they both use trapped ion systems using the ytterbium ions. And the most recent is from 32 qubits from IonQ and 10 qubits from Honeywell. And something we'll come to on the next slide, both of these machines actually have pretty impressive quantum volume. And some links there if you want to see more information. The picture on the right, this actually shows the geometry that's used in the Honeywell computer. You can see it has a sort of T-like shape that they actually have to do it. As you can imagine, right, you can see we have all these different quantum computers made of very different technologies. And what this means is that if you really want to ask the question, which is the most powerful quantum computer, that's actually a question that's far from trivial to answer. In fact, it's very tricky to compare the performance of quantum computers. Firstly, we have all these different technologies that are used to make qubits. And so if you just want to compare number of qubits, they actually end up having dramatically different performance. You need to worry about things like the qubit lifetime, the gate fidelity, the gate operation time, and the connectivity to do it. And so it's really, I would say, it's an active field of research, thinking about how do you want to do it. And I've linked, for example, one paper here talking about a research project that was done to compare the performance of two different systems. So one of the metrics that gets talked about is known as the quantum volume. And it's actually one that came from IBM. And it kind of depends mostly on the speed of the execution and the error rate. It sort of represents the maximum size of square quantum circuits that can be run. That's actually one of the reasons why people maybe debate whether this is the best metric to use, because in reality, not all the circuits that we might want to execute on a quantum computer really are square. And so this is maybe not necessarily the best way to do it, but it's a metric that we have. And if we use that, if you take a 27 qubits IBM computer, you end up with a quantum volume of about, they've achieved a quantum value of 64. Honeywell has achieved 512, and IonQ just recently said that they've actually achieved one of 4 million. Now, of course, what you can notice here is that these numbers grow really rapidly. I think it's also the case that one can actually tune the type of quantum computer that you build in order to maximize this measure of the quantum volume. Nonetheless, it's something that we do have, which can actually be used for comparing different computers. Now let's move on to talking about quantum algorithms. The first point that I want to make is that it's actually really hard to develop a new quantum algorithm. In fact, it's so hard that all known quantum algorithms are listed on a web page, which is called the Quantum Zoo. I have the link there, and I've kind of taken a screenshot of the top of it. And yep, it's the case that all quantum algorithms, you can pretty much find them on one web page, which is very different if you think about classical computers today. Another reason that it's hard is because a lot of people think that it's only useful to run an algorithm on a quantum computer if you're either running one that cannot be run on a classical computer or where a quantum computer is expected to achieve exponential speed up. So many people are not interested in just running anything. They're only interested in running ones where you can actually prove that the quantum computer is better. Other reason it's hard, programming for quantum computers is really done at a much lower level than for classical computers. And you really do need to worry about the individual bits and gates when you're thinking about how you want to do the programming. It's kind of similar for anyone who's done programming in assembler. It's a similar experience if you want to program a quantum computer. But the reason why we're interested, well, one of the reasons why people are interested is because certain problems which are difficult classically actually turn out to be easy on quantum computers. And that's really interesting. It's saying that here we have this different paradigm of computing. This might actually allow us to do things that we're not able to do or we're not able to do easier. And one of the examples we'll come back to a little bit later is factoring with its super polynomial speed up. Another one, we talked a bit about this yesterday, is the fact that you cannot efficiently simulate a quantum computer on a classical computer. It's actually, in fact, it's expected to be hard due to complexity objects. And so here's a simple sketch about how you might want to think about it, is that we hope that all the algorithms that are easy classically might be easy quantumly. And then we also have algorithms which are hard quantumly. So it's really expanding what we're able to do. So here we go a little bit further into the topic of algorithmic complexity. And here's a picture which shows you the various different classes of algorithms. I'm sure you've heard about P and NP. This is about whether algorithms which can be solved in polynomial time, that's P, and NP is algorithms that can be verified in polynomial time. And people don't actually know if those are the same or different. In fact, that's one, if you can solve that problem, you're going to win $1 million. So that would be pretty nice. But of course, there's a bigger class. They're actually all sitting inside P space, and that would be all problems which can be solved on a Turing machine using a polynomial amount of space, not time. Then, of course, you have these NP complete, which are just a subset of the NP, which actually are representative of all the different problems in NP. Now, where quantum computers come in is you add this class BQP, so that's the one in the sort of light gray. And what that one is representing is the set of problems that can be solved on a quantum computer in polynomial time. It has the acronym stands for bounded error quantum polynomial time. And so the question here is BQP and P disjoint, right? Are there other problems that we can solve? But perhaps more interestingly, people wonder, does BQP actually extend beyond NP? Are we really expanding this area in which we might be actually able to solve problems? These are questions, and these are ones that people are researching in complexity theory and really trying to solve. We talked a bit about this yesterday as to why people are excited about quantum algorithms. This is because they promise things like exponential speed up, pattern recognition, or Fourier analysis, efficient searches, minima finding, matrix mathematics, things like machine learning. We'll talk about that a lot tomorrow, linear algebra. And of course, we have these challenges. When we're thinking about our algorithms, because the quantum computers today are already in this NISQ era, we have to worry about things like decoherence, the short lifetime of the qubits, the noise. We also often need to use significant classical resources to be able to interface to quantum computers. We need to worry about things like I/O and even things like error correction. So let's go into a few of the sort of more famous examples. So the first one is the quantum Fourier transform. And what it actually is, this is one that was written in 1994 by the original implementation by Don Coppersmith. And it's really the quantum implementation of the inverse discrete Fourier transform. So you just want to do some sort of mapping from one space there into another space. Now, the reason why it's interesting is that it turns out that the quantum algorithm is exponentially faster than the fast Fourier transform. Hopefully you've all seen this big O notation. It's just simply showing you the worst case scaling of an algorithm as a function of the number of inputs. And so you can see that you go from an algorithm, which is on the order of n to the n, down to order of n squared, which means you're removing this exponential. And so that as you get to bigger and bigger data sets, this is going to be much faster. However, that's slightly overselling this. Because if you recall, right, we were talking about quantum computers and how you might have all this information in them, but you do need to worry about what you can actually measure. And so it turns out that for this algorithm, despite being very fast, you're actually only able to measure one of the n components. And so perhaps a more accurate way to talk about this would be known as quantum Fourier sampling. So you can do a Fourier transform for all of it, but you can actually only figure out what is one of the components. And the way it's done is it's really a generalization of the Hadamard transformation, which we talked a little bit about yesterday, through the addition of phase. And here's actually the matrix really writing it out, where you can see, and here these omegas, these of course are the different complex roots of unity. Now, the quantum Fourier transform is actually used in many different quantum algorithms, except in fact, some of the ones we're going to talk about today, for example, Shor's algorithm. It's also used in quantum phase estimation to do it. And I think it's a really nice example because, as I mentioned, it shows you this demonstration, this nice demonstration of the tension between the speed of execution and the problems of the measurement to do it. And yeah, so now let's move on to the next slide, where you can actually see one of the circuits for the quantum Fourier transform. And as I mentioned, it's sort of a generalization of the Hadamard. So you can see that it's combining together the Hadamard and the control phase gates. And then you need to do it, of course, for the various number of qubits. Then, of course, finally, you would need to actually do the measurement to actually get your result. Probably the most famous quantum algorithm is one that's known as Shor's algorithm. Peter Shor, he's a professor at MIT, At the time when he actually wrote this algorithm, he was working at Bell Labs. And this is probably the algorithm that really stimulated significant interest in quantum algorithms. And what it does is it's simply an algorithm for factorization. However, as I mentioned yesterday, the reason that people get excited about it is all the implications for cryptography. Now, the way that it works is you're just trying to solve this sort of very simple to state problem, which is if you're given an integer n, which is equal to p times q, where p and q are primes, you want to determine what p and q are. And as n gets large, this becomes very difficult and very slow to do. You can see here that the best classical algorithm, which I linked, it's one that people are very actively working on, has this execution time, which grows really exponentially with n, meaning that, of course, it takes a really long time. However, in Shor's algorithm, the execution time actually is just log n cubed approximately. And so you can see that you have this dramatic speed up over the classical algorithms. As I mentioned, many of the currently used cryptography algorithms, things like RSA, public key, they rely on the fact that factorizing these large integers into primes is very difficult. And that's really what's protecting basically everything that you do, right? Things like banking on your computer, etc. It's what it does. For example, classically, a 768-bit number was factorized with hundreds of computers over 2 years, taking something like 10 to the 20 operations. Whereas if we use a quantum algorithm, one could think about factorizing a 2,000-bit number, factorizing with a billion qubits and 10 to the 11 gate quantum computer in just over a day. Of course, we do not have such a quantum computer just yet, but it sort of shows you the scale that if one could build one, then you can really go far beyond what we're actually able to do classically. Now, in terms of the implementation, it relies on reducing the factorization problem to be a special case of the hidden subgroup problem, which is linked there. And in fact, if one found more general solutions to this hidden subgroup problem or for other groups, it would actually imply that other cryptographic systems would also be broken. It can be broken down into two parts. Firstly, what you want to do is you want to reduce the factoring problem into a problem of order finding to do that. And this is really just the order of the integer is something that comes from modular arithmetic. So if you want to find the order of some integer x mod n, you just want to find the smallest integer r such that h to the r equals 1 mod n to do it. And once you've done that, then you actually want to use a quantum algorithm, which can actually solve the order finding problem. And it's interesting how the algorithm works. Effectively, what you actually want to do is you pick a random number for this quantum part, and then you need to compute its order. If the order turns out to be even, then you've actually found one of your solutions. If it's not, then you actually throw it out and you start again to do it. And this quantum part, of course, you may sort of be thinking about this, hey, this sounds a lot like that Fourier transform that we were talking about. Indeed, that's correct. The quantum part of this algorithm actually relies on the fast Fourier transform. So and again, it's sort of similar to the last one, right? Where it's not necessarily perfect how you do it. It can be very fast, but in certain cases, you might have to try again. But the probability is something like 50% to succeed. So typically, it's not very many times that one would need to try. Next, we come to Grover's search. So Grover's algorithm targets searching for a specific element within an unsorted database. And the way that it works is you do a uniform superposition over all possible solutions. And then you want to destructively interfere states that are not solutions. Perhaps another way to think about it is this image on the right, where you can imagine taking your space and splitting it into two parts. So you can see E and you can see A. A are actually the solutions we want to find, right? So it's some elements, so it's a very small fraction of the space. E is the rest of the space. What you do is you start up by defining your state psi, and you'll notice, of course, that psi lies very close to E because that's a large fraction of the space. And then you actually perform transformations, and your goal is ready to get psi to point to A. And in fact, the way you do it is you use two different parts. you do a reflection about E, and then you and this and then you do a reflection about psi to do it, and that effectively gets you there. It's sort of another way of thinking about how you might actually do it. Then at the bottom, you can actually see what the circuit will look like. And indeed, that diffusion operator, that's actually doing this reflection around psi. And then you can see the other components within the circuit. Now, Grover's algorithm is not quite as impressive in terms of speed as Shor's. The classical solutions here are order n, and the quantum solutions are order root n to do it. So the speed up is much less. However, it's of course applicable to a wide range of problems. And so that's why people are particularly excited about it. It has been extended later on by Long to become the Grover Long, which has really a zero failure rate. As I mentioned, the algorithm is really very versatile and can be used as part of more complicated quantum algorithms. Some of the examples include finding the minimum of an unsorted list of n integers, that gives you quadratic speed up, determining graph connectivity, pattern matching, finding a match pattern of P of length m within text T of length n, and many others. And so that's why it's a very useful algorithm. The last thing I want to say about algorithms is, in fact, that sometimes when one wants to go and solve a quantum problem, you actually end up finding things that impact classical algorithms. And here's an example that I found from one of my colleagues, which actually shows you that the problem to solve is if you have a sample preference matrix T for users and products, and you want to try and generate suggestions for a user, you know, what products should I buy on Amazon or things like that to do it. And so people set out to try and solve it using these sort of quantum recommendation systems. And you can see the paper that came out there. However, the challenge was to try and prove it was actually the best algorithm to do it. And so someone set out to do it. And the actual result was they ended up with a better classical algorithm, which is what you can see here in the paper on the bottom left. So sometimes trying to solve quantum problems may not necessarily find you algorithms better. It may end up actually improving your classical algorithms. So we've been talking about algorithms. You may be wondering, let's get practical. How can we actually do it? The field of quantum programming languages, I think, is still in a very early stage of development. As I mentioned, it's rather like programming an assembler or for hardware rather than using modern programming languages like Python or C++. You really do need to think about what circuit you want to make, and you need to actually program the gates for the circuit explicitly. Pretty much at the moment, every vendor has their own programming language or software development kit. In many cases, though, the interface will feel familiar. It's via Python. And so some of them are at rather early stages of development, which means that regular debugging required. And often, for example, you'll be writing some code and you'll find that things just don't work. You actually have to contact the developers and get them to help you to fix it. Really is something that's at quite an early stage. Some of the examples that you can have a look at if you're interested are Qiskit, which comes from IBM. There's Cirq from Google. Eways has the Ocean SDK. Rigetti have Forest SDK, also using Quill. On this slide, I pulled out a couple examples to show you what it might look like. You can see it looks very familiar. It looks a lot like it is Python, of course. On the left, this is what it looks like for Cirq. On the right is what it looks like for Qiskit. And you can see that you really want to do things like, you know, pick your qubits, create your circuit, maybe you want to simulate your circuit, then you can print the results. On the right there, you can actually see the circuit that this very simple example has. So obviously they end up having pretty similar structure. And something to know is that in many cases, it's pretty simple to get a small amount of time to run on real quantum hardware. In many cases, companies will give you a few seconds, but of course, seconds on quantum hardware can actually do quite a lot. And it's generally possible to register for free accounts to do it. And so I would say it's still at the stage where people are very interested in having those who want to really use their hardware and use their different languages. I really am hopeful that this will improve as time goes on, that we might end up with common interfaces and common languages that we can actually use for quantum computers, because of course it's really interesting to be able to ask the question, you know, can I run the same algorithm on different ones without having to write completely different code to do it? A very important topic is quantum error correction, because all the currently available quantum computers are really extremely noisy. That's that N in the NISQ. And so it means that if you're trying to run your algorithm, there is really a high potential for errors to occur. As we discussed, it's rather like a catch-22. The noise is induced through outside interaction, yet we need to interact with a quantum computer for input and output. Of course, this isn't a new topic. For classical algorithms, we typically use redundancy to mitigate errors, but this is, of course, not possible in its most simple form due to the no-clone theorem. But instead, what we can do is we need to spread the information on a single qubit onto a number of qubits. And here's a very simple example for a circuit that can be used to correct for a single bit flip. You can see the qubit that we're interested in. That's the one there at the top. And then we add these two additional qubits. We can actually entangle them and spread the information between them, perform some operation, and then basically repeat these operations again. And essentially, if you go through it and you sort of go through if it was 0, if you go through if it was 1, what you actually find is this can actually detect the single bit flip code and actually correct for it to do it. Now, one important thing to know is that this actually relies on the assumption that the bit flip rate for a single bit is actually low. Of course, if it becomes too high, eventually some of these algorithms actually break down because you start having the probability that many bits can actually change. So that was a simple example for single bit flip. This is actually more complex, and this comes again from Peter Shor, who was the one from the quantum factoring algorithm. This actually shows you a more general error correcting code, and it can correct for a bit flip, a phase shift, phase flip, or both to do it. And if you're interested in learning more about this very interesting field, I linked a tutorial here. There are other methods that can be used. For example, the bosonic systems, which we'll come back to just a bit later, they have special algorithms. And there's one that have a beautiful name. They're actually called the cat states. And that's because they're actually named after Schrodinger's cat. Then there's also GKP, which is named after the authors Gottesman, Kitaev, and Preskel. Of course, the one that people are really excited about for sort of long-term or even more error robustness, and not just correction, are these ideas from topological quantum computing. If you're interested, there's this classic paper by Kitaev, which tells you about how this could actually be done. Now, probably one of the earliest applications of quantum computers will be quantum simulation, which was indeed one of those original motivating ideas. This is the quote from Feynman: "Nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical." And it's probably likely to be one of the earliest useful applications of quantum computers. And one can imagine a bunch of different quantum simulations for things like quantum chemistry, superconductivity, metamaterials, and indeed high energy physics. And I'll show you one of those examples from some colleagues tomorrow. Typically, what one has in mind for this is to really calculate the dynamical properties of the system from the Hamiltonian using the Schrödinger equation. And you could envision using a large digital quantum computer for such simulations. You could also use an analog computer to use one quantum system to mimic another. If you're interested in learning more, I've linked an overview there. Here are some of the examples of things that people have done recently. For example, there's this paper in Nature where they actually simulated the beryllium hydroxide molecule. The top right, this is a water molecule simulated on a trapped ion quantum computer. And on the bottom, there is a hydrogen using a VQE to do it. And so you can see that we're still at the state where people are simulating, simple, small molecules. But nonetheless, it's really interesting because it shows the promise of being able to learn things about molecules that we don't know. One of the pretty recent ones that was done was using Google's Sycamore computer. And please don't ask me what isomerization is, but I'm pretty sure it's something that the chemists are very interested in. And so what they were doing is they were studying this isomerization of diazene using a variational quantum eigensolver. And so there's a sketch there showing how they actually set this up. And what they're actually doing is they're running Hartree plot calculations of molecular electronic energies to do it. Now, maybe fortunately, maybe unfortunately, this is actually something that can be done very efficiently on a classical computer. But that's actually good because it means that they can actually use this to demonstrate that the quantum computer is actually doing the right things. And you can see, for example, on the bottom right here, this is actually showing you this calculation of the energy. And you can see the curve, that's really the classic, the prediction, what we expect. And then these points, these are the various different values from the supercomputer calculation. And you can see when you start out with the raw, you're not doing very well, but in the end, they actually get to this excellent modeling. And then you can actually see on the left, that's actually showing you some of the performance of the quantum computer in doing that. Now, the last topic I want to talk about today is something called quantum advantage. And as I mentioned, when people are developing algorithms for quantum computers, the goals tend to focus on either these algorithms' potential for dramatic speed increases or algorithms which cannot be solved on a classical computer. And the latter is referred to a term coined by John Preskill at Caltech, which is defined as follows. And it's often, in its first incarnation, was called quantum supremacy. The definition here is that this is the point when quantum computers can do things that classical computers can't, regardless of whether those tasks are useful. So before we get to the name, look at the sentence and let's unpack it for a bit. The point is you really want to demonstrate that it can do something that you can't do in a classical computer, but you don't actually care if that's useful or not. So sometimes people talk about this and say, once we've demonstrated it, this means that quantum computers are better. Doesn't mean that. It means that there is a specific task where a quantum computer can do better than a classical computer. Now, you notice, of course, I'm using quantum advantage, not quantum supremacy. That's because this is an alternative term in use and avoids some of these political connotations. So I'm going to stick to that today. In the literature, as you'll see, it's actually mixed between the two terms, but they really do mean the same thing. Now, in October 2019, Google published a paper in Nature in which they claimed that they had achieved quantum advantage by solving a problem in 200 seconds on that Sycamore chip that would take the largest supercomputer in the world at the time, it's not the largest anymore, which is Summit, is actually in the US, 10,000 years. The problem, as you might guess from what I talked about on the last slide, is not necessarily very interesting. In fact, what it is sampling numbers from a pseudo-random quantum circuit to do it. And here's actually the sketch of the abstract, and you can see the link to the paper in Nature to do it. By the way, that 200 seconds might not sound particularly impressive. In fact, to do that, they were sampling this quantum circuit that they have on Sycamore 1 million times within that 200 seconds. And it turns out if you want to do an analysis of how long this might take classically, computing this probability distribution ends up becoming exponentially more difficult with the number of qubits, and which is the width, and also the number of gate cycles, which is the depth. Here's one of the plots from their paper, which is actually showing you how they verified that they knew what they were doing. So on the left, there's in a sort of classically verifiable regime, and you can see that they're doing a number of different verifications of the circuit fidelity using different methods. And they're doing that as a function of the number of qubits. And overall, you would say the agreement is pretty good. Then on the right, as you start increasing the number of cycles for these 53 qubits, then you're actually entering into the supremacy regime where you can't necessarily do this classification as before. But overall, that looks pretty good. So the responses were fairly dramatic to Google's claim. One response came from IBM, which was on their blog, and they stated, "We argue that an ideal simulation of the same task can be performed on a classical system in 2.5 days." And the reason that they argued this is that they said that in this calculation of determining these 10,000 years, people hadn't thought about the fact that there's a whole lot of memory available in Sycamore. And so you could actually store a big lookup table and you could actually make it a lot faster. Work has continued. For example, on the right here, this is one which came out last year, which was doing this classical simulation of quantum supremacy circuits. And doing that, it was a more detailed one than this response from IBM. They were saying that it could be done in less than 20 days on Summit. And if you were doing something more modest, you could reduce it from years to minutes, running several times faster than Sycamore itself. One thing to comment is the fact that none of these were actually done. The problem is that using these big supercomputers, you can't actually get them to use entirely for yourself. So in many of the cases, these are responses that had to be done based on sort of arguments about what might happen. Then actually this year, there was a new result which came about how to actually do the simulation using 60 GPUs. And they actually found that they could generate 1 million correlated bit sprints, and which was actually doing better in terms of fidelity than quantum supremacy. So as you can see, there were pretty strong reactions. Of course, one you would have expected from IBM because they were, of course, trying to do the same thing. But then also people trying to really answer this question, was the problem as difficult classically as Google might do? And so there are a number of different opinions. I would say there's an interesting article there if you want to have a look at it. It's by Scott Aronson from UT Austin, which talks about it. And I think that if you ask me my opinion here, I would say that perhaps Google were a little overambitious to claim that they'd obtained quantum advantage, right? However, it's definitely the case that we're extremely close. Because of these things, growing in terms of exponential time, if we imagine that you had a supercomputer with just a few more qubits, then it's clear we'd be well beyond the regime. So I would say that maybe we're a little bit early, but we're certainly really at that point. And so that means that it's pretty exciting in terms of the development of quantum computing. Then one other one on the same topic is from just last year in December 2020. The team from that USTC in China, they actually claimed that they had obtained quantum advantage using boson sampling to do it. What you're trying to do here is, again, not trying to make it useful. You're trying to calculate the probability system of the probability distribution of a system consisting of many bosons. It turns out here that classically, the solution time increases exponentially to do it. So similar to the problem we were just talking about here. And what you can do with a photonic quantum computer is you can really simulate the process directly. You can allow the photons to interfere, and then you can sample the distribution. And you're really encoding the information in the system in the positions and the polarization. The time it took them was 200 seconds, and they claimed that it would be 2.5 billion years on China's Taihu Light supercomputer, which at this time was the world's 4th largest quantum computer. I would say this one, there's kind of no debate, or at least I haven't seen any debate yet, that here we don't have a chance for a classical computer doing the same thing. Yet at the same time, of course, this is a quantum computer built to solve one problem, and precisely this problem. So we are at the stage where we can build quantum computers that can solve problems that classical computers can't, but we're still some time away from getting to generally useful classical computers, which can solve many problems that classical computers cannot. So in conclusion, I hope I tried to show you that developing quantum algorithms is very challenging. Only a handful of algorithms exist, and they're still all listed on a single web page. Try to give you a brief introduction to some of the most important algorithms, things like quantum Fourier, transform, Shor's factoring algorithm, Grover and Grover-Long search algorithms. Also discussed one of the probably most promising, likely early useful use case for quantum computers, which is quantum simulation. Quantum advantage has been a target for quantum computation for many years, and it can be argued that it was achieved somewhere in 2019, 2020. And finally, we also had a few slides about programming language, SDKs for quantum computers, as well as quantum error correction. Thank you.
Thanks to you, Heather. So, as we did yesterday, I will read the questions from the chat, okay? And then if someone would like to do it by voice, you can raise your hands. And already I can see one hand here. So I will give, I will give the turn to Richard. Please, Richard, go ahead.
Thank you very much. Thank you, Heather, for your talk. I have a few questions on the photonics.
Sure.
Would you have a number in terms of the quantum volume on the Xanadu computer?
Unfortunately, I did not manage to find it. I would say, of course, perhaps it might exist in Chinese, and I was not able to find it. Honestly, the information that I could find about that computer was extremely limited.
No, the Xanadu, the Toronto one.
The Toronto one.
It has
Sorry, I
like
thought you
6
meant
or 8 qubits.
Yeah, I don't have that number. I can look. I'm sure that exists because people have bought those. So I imagine that it definitely does.
And the 2-gate operations in the photonic computer, how is that realized?
Okay. So I don't have a slide for that, but I believe it's the same as we were saying for the single ones, right? Where you can think about having these combinations of splitters and mirrors, right? And you can actually do that many different times to do it. I don't have a detailed example about how exactly you would do that, but I can imagine that it will be a simple extension of that process.
Okay, thank you.
Now I could see Julian Baglio, so please go ahead.
Hi, Heather. Thanks a lot for the lecture. Actually, I asked the question on the chat, but I prefer speaking up because maybe it will be clearer. I'm wondering if there are any ideas or already like built genetic quantum algorithm. And what I mean actually here is more a hybrid scheme, much as for VQE, in which you have like a quantum algorithm, which does one part of what you want, then you do the measurements, and then the output of the measurements is fed into a classical genetic algorithm. And then you can backpropagate the final results at the beginning and you iterate to obtain the answer you want.
I don't have an example to hand, but I'm pretty sure that such a thing exists. Indeed, what you're describing is how many of the actual more practical applications of quantum computers are done, right? Because as you can see, the power is super limited. So you can do way better if you follow a procedure like you discovered. I think I came across one of those when I was preparing the lectures, but unfortunately, I don't think I put the link in. I can have a look for it and try to send it to you if you like.
Yeah, I would be interested because, I mean, I've seen many, I mean, not many, but I've seen a few quantum algorithms, of course, doing this hybrid, but I've not seen anyone also like building it together with the genetic vision, like trying to merge using the genetics rules, the solutions to obtain a better one.
Yeah, no, it's a very natural way to think about doing things. I think it makes a lot of sense.
Thank you.
So then I can see another hand from Stephen Nicholas.
Yes, hi. First of all, let me say thank you for this wonderful lecture. You spoke a little bit about increasing size of quantum computers and quantum chips. Are there any sort of problems that are foreseen or that are already happening with expanding those chips sort of to arbitrary sizes like you would a CPU, or are there no known limits on how you could expand those?
Oh, I think there are many limits. And in fact, I think we're seeing some of the limits even in the quantum computers of today to do it. So it was all the things that I was actually talking about, right? It's about the time that you can actually keep the information of the qubits, it's the noise, etc. All of that gets worse as you want to increase the size of it. You also have problems, and that was a little bit, I think, what IBM are thinking about, is how you even think about doing the readout as you try to improve, as you try to increase the size. You start getting to all sorts of limitations. Another one is many of them need to be kept very cold. And so you start running into limitations of the size of the dilution refrigerators that you can buy. And so I saw some really interesting pictures where IBM are trying to build new dilution refrigerators that can be much bigger in thinking about doing it. So I would say it's actually the opposite. I think it's absolutely far from clear how it's going to evolve. And I think there are many problems that need to be solved at each step. So it's not, you know, IBM have said they're going to double the size of the quantum computer every year. I think that in order to do that, they have to solve very many problems every year to be able to get there. I think it's extremely hard to do it.
Okay, thank you.
I see here in the chat the first question from Vivek. Which qubit architecture is efficient?
Sorry, I'm not sure I understand the question.
Which qubit architecture is efficient?
So, efficient.
Efficient, yes.
I'm not sure I understand what he means by efficiency here.
Me neither.
Vivek, you want to speak up?
Yes, Vivek.
Okay, maybe he'll follow up later.
Maybe, yeah. Okay, let's go to the next one. So then from Logan's, how do people research if BQP is extending P if it is unknown if NP is extending P? Are they only looking for algorithms that are BQP and not NP?
I managed to lift up the chat. I'm glad I did. It's hard to read out all the different acronyms.
Yes, it's good because with the acronyms.
Yeah, so thanks, Lawrence. It's a good question. I think that in many cases, what people are trying to do here is you can actually do proofs about the existence of algorithms without necessarily have the algorithm itself. And in fact, that's a lot of what gets done in complexity theory. So my understanding is that's how they're trying to answer this question. But you're right, if we don't know that, you know, if you could actually prove one, you're essentially proving the other. So I guess that's also why people are really interested, is if you can make a demonstration like this, of course, there are corollaries in what you've actually proven. It's interesting, I was reading up a bit on this somewhat recently, and there seem to be a lot of different opinions about which way this is actually going to go. And so I would say it's far from clear that even if we don't have a proof, even if we have a good knowledge of how this is actually going to be solved, many people are saying that maybe it's not going to actually be different, and that the only advantage we get from quantum computers might be a speed up, but it's something that's debated.
Okay, so then from Roman, I don't know if, okay, no. So from Roman, if the IonQ computer contains 32 qubits, how many gates are in there?
I do not know. They did not, they were, as I was saying, the companies are secretive. IonQ did not release very much information about their quantum computer.
Okay, and also I can see Dimitrios, I think from yesterday, he was writing a direct message from me, but he wanted to raise his hand. So Dimitrios, just go ahead if you want.
He's still muted, I think. I can see him talking.
Okay.
He's still talking. We need to unmute.
Yeah.
Okay.
Now,
okay.
Now you're unmuted. Now
Can you hear me?
Yes.
Pardon me for my ignorance. I just wanted to ask if the academic community or companies have decided which metric system for the information in quantum computers is going to be used.
Can you repeat it? It was a little bit broken up, a very key part of your question.
Yes, if there is a decision on which metric system on information is going to be used in quantum computers. Is there anything definitive about the metric system of information? Like in normal computers, we have bits, bytes, megabytes, like it's a metric system. So if the community or the companies have come to an understanding and they did, they have a decision of the system that they are going to be measured or worked. No, nothing. This is what I wanted to ask.
I have not seen anything like that, so I suspect the answer is no. And I think the reason that the answer is no is because at the moment we have such few qubits that it doesn't become relevant for anyone just yet, right? You know, if you're talking about 20 qubits, we don't need to worry about that at this point in time. On the other hand, right, it's something I mentioned yesterday. We don't even know if we're going to keep using qubits, right? One could think about using extra energy levels. You could think about a 3-level system. So I'm not sure. I mean, at the moment, that's what most people are pursuing, but it's not even obvious to me if we're actually going to be stuck with, you know, bits of zeros and ones. Maybe we're going to actually use something with higher order. I think that's not yet known.
Okay, and now here, I think I can, do I have a chance to have a second question, or there's someone else waiting?
You can.
I think you can.
Second.
Okay. This is because I was trying to rephrase, I apologize, to rephrase what I was thinking yesterday. And I saw also in one of the slides over here that you talked about, again, about I/O. Why should we worry about I/O if it's quantum computing? It's neither I or O. This is what I don't understand.
All I'm talking about, okay, I'm using the term from regular computing there. But of course, when you want to actually use a quantum computer, right, if you want to solve some problem, typically you need to interface it to a regular computer to put that information on it. So you need to think about I/O in the sending info from a regular computer to a quantum computer and getting it back. That's actually what
okay, that's great. Now this is much clearer. Thank you very much.
Thanks for the question. That's true. I hadn't thought how that might be confusing. It's correct.
Yes, no, because this is everything really interesting, but this is why I was asking about swap yesterday. Normally you use swap if you need to increase well, in a normal computer, you don't have space. You don't have space allocated in the memory, so you use swap. You know, I just thought everyday computers. I'm not in this deep thinking that you have. But I thought, why using swap if you don't have any I or O? You know. Okay.
Yep.
Thank you very much. Thanks.
Okay, thanks, Dimitrios. So you can just move. Okay. So then from Baptiste, are there advantages in image processing with quantum processing?
I think we don't know the answer to that yet. I haven't seen someone trying image processing on quantum computers. I suspect there may be an advantage. Because there's a very active development into machine learning, which is often used in various different algorithms for image processing. So as that becomes realized, I could imagine that there might indeed. But I think we don't have enough qubits really to even store images on quantum computers just yet.
Thanks.
And now from Tassos, do you believe that in the future we will use a hybrid of classical and quantum computers depending on which algorithm is most efficient?
Gosh, that question assumes all sorts of things. So I'm not even sure I'm willing to state that we're definitely going to be using widespread quantum computers in the future. I think that all depends on what happens in the next few years to do it. But if we assume that quantum computers do work, I think that it's definitely the case that for a long time we would use a mix of the two, because there are going to be certain things that would be easier on classical and certain that would be easier on quantum. In the very far future, which is of course impossible to think about, it's not obvious to me if we might imagine a world where, you know, on your desktop you have a quantum computer. At the moment that seems insane, right? I can't have a dilution refrigerator sitting in my apartment to do it. But who knows, it's difficult to think about it. But I do think that in the intermediate time scale, it's likely to even have hybrid algorithms, right? And then we might think about using one for certain applications and some for others.
Yes, I think hybrid will be the way, yes, but I don't know. Then another question from Maria Dimo.
Yes, thank you very much. Can you hear me?
Yes, and see you.
Thank you. You partially answered on your last answer to Tassos, but I'm still worried a bit. If the companies, for commercial competitive reasons, ambition, IBM who says we double every year, or military applications, which presumably already on this, make mistakes, will there be a scientific community that they would listen to, that would give them advice? Because I'm not sure that they would know what they're doing. I'm talking especially about the military applications.
I think that's a good question, and I don't know if I have a good answer to it. Indeed, there are already military applications ongoing. This is known to do it, because obviously, right, when you think about the cryptography, right, that has very obvious implications throughout. And it's true what you say. Like, in many cases, scientists are leading the way, right? You know, we'll be developing a new technology, but this one's happening in a strange way in which the companies are building the quantum computers. Now, don't get me wrong, there are many universities, many research groups who are also building pieces of quantum computers. And so that's certainly something that's happening. In fact, people here at Berkeley are doing that. However, it's very hard to compete with the resources that these large companies have, right? And so that's why it ends up being in this unusual state where the big quantum computers are getting built first here at these labs. So that's a sort of negative way. But on the other hand, I would also say that many of these companies are interacting with academics. And if you look at them, it almost feels like they have academics working at their companies and things like that. You know, they present papers, they publish in Nature, they go to conferences and things like that. So if I want to be more optimistic, I'm hoping that one heads towards a model, right, where there's sort of more integration between the two, right? So maybe they're funding it, maybe they're doing the research, but they're functioning like researchers, and there's usually peer review, there's discussion, and that would be something that could help, right, to drive towards the future. So those are my two kind of answers to your question.
Thank you very much. Thank you.
And now one question from Luis, but here in the chat. Any estimated educated guess on how long it may take to have a quantum computer able to break financial or cryptocurrency, cryptographic signatures?
Yeah, so I sort of had one hidden in my talk because I gave you that number of 1 billion qubits, right? That would be able to factorize 2000 length primes. So that's sort of a scale, right? So it really just, it's very, in a sense, simple. It depends on how long is the number that you're using for the encryption. And then you can ask how many qubits do we need? But at least what I can tell you is that we're a good deal away from it, right? We're still in the regime where we're talking about a few hundred qubits. So it's at least many years. And one thing I unfortunately just didn't have time to fit in here is that there are most definitely ideas about how to do quantum cryptography instead of classical cryptography. So I think if this comes to be, right, if we start getting near that regime, I think what we will see is that we will actually start using those algorithms instead of our existing ones. There is one thing that someone pointed out recently, which made me think, is that people may be storing this information already now, thinking ahead to the prospect of being able to break it, right? So if you're sending, messages to your friend and then someone's downloading them all encrypted and waiting for the day, it could easily be the case that things that are happening now might get broken in the future. So that is something to think about. But I think it's significant amount of time, if ever. It really depends on how technology evolves. Okay, so now, last question is just popping up. Does quantum, from Mikhailo, so does quantum error correction reduce available qubit space for user applications? Do we need to care about it while implementing any algorithm using SDK? Or it becomes more crucial as a problem size increases? The answer is most definitely yes. And so there are a couple of different ways of doing this. I showed you some of the quantum error correction algorithms directly. And there you could see, for example, like for the bit flip, we needed to use 3 bits to actually store and error correct 1 bit of information. So it most definitely reduces it. One way that people think this may evolve in the future is you can have physical qubits, which are the real qubits in your quantum computer. And then you have the logical qubits, which you can use for your algorithm. And they would be reduced by some number and perform for you automatically the error correction that you need. So if that comes to be, then you need to care less. At the moment, you do need to worry about it right now, because in many cases, there's no such automatic error correction available.
Okay, Vivek is writing again, the one about the fission. So as earlier mentioning, companies using different qubit architecture like superconducting qubit, trapped ion, photopolarization, etc. Why so? Is there any kind of feasibility difference with respect to qubit architecture?
So that's a good chunk of what I was trying to talk about in yesterday and today's lecture. Yes, there are many differences between them. And I think the reason that companies are trying these different technologies is we don't yet know which is the one that's actually going to work, right? If we knew that, then it would be kind of obvious and we just go ahead with that. I would say that the two kind of leading ones are the superconducting qubits and the trapped ions. But then you have these other ones which have promised that they might be much more scalable in terms of building bigger quantum computers. But I think we're just at an early stage. And then at an early stage, you really need to investigate and try all the different technologies. And by doing that, you can actually figure out how to do it and which are the ones that are actually work. But I think we don't know yet. Otherwise, everyone would just do the same thing.
He's saying thanks. So I don't see more questions in the chat and neither more raised hands. So I guess we can finalize this session. In fact, Dimitrios was saying, great lecture, congratulations, Heather.
Thanks, Dimitrios.
Some claps. So thank you very much, Heather. And if you want to say something, apart that you are here tomorrow again at the same time. So please, if you
I think nothing more. I'll put up the slides later on in case anyone wants to have a look at them. And otherwise, I'll see everybody tomorrow. Same time, same place.
Thanks.
Thank you.